Hey calculus students, these notes are on differentiation rules. So to contextualize this, in this past week we've been using the limit definition of the derivative in order to find the values of f prime for specific functions. And in doing so, we've also been noticing some patterns. So this is just a version of the table you already have in your notes. You don't have to put it in here again. But just remember that we started noticing some patterns. So first of all, with linear functions, we saw that the derivative was just the slope of the linear function. With x squared or quadratic functions, we sort of were noticing, the exponent is coming down out front. And in with 5x squared, it's getting multiplied with the 5. So 2 times 5 becomes 10, and then your exponent gets bumped down. Similarly with x cubed, the 3 comes out front, and we have a new exponent of 2. So it's kind of like bumping down the 3 to a 2. So we're going to kind of formalize some of what we're noticing here and look at some examples, and then also see how these differentiation rules can allow us to find derivatives that we were unable to find using the limit definition because our algebra can only take us so far. So first of all, just to define the idea of differentiation, we've talked about being differentiable. So differentiation, we will define as the process of finding the derivative of a function. Sometimes we'll also say taking the derivative of a function. Okay, so now I'm going to start with the first rule we're going to have is something called the constant rule. And this actually isn't even in our table, but it's this idea of what happens if I have some function that is constant. So like f of x equals c, where c is a number. So graphically, we can think about this as being some horizontal line at the y value of c. Okay, and the idea, so then if I wanted to find what is f prime of x when x is just a number, well, if we think graphically, we can say well, we know that the slope of the tangent line at any point on this line is 0. So we're going to say now we have something called the constant rule, which says any derivative of a constant number is exactly 0. We know this, again, just to annotate what I just said, we have slope of f of x is always 0. Okay, so that's pretty simple enough. We're a lot of times using that in conjunction with some other rules. So for example, there's a constant here. So we're saying 2/3 x plus 3. So if we think just about the derivative of that 3, it's going to be 0. And we don't see any value, second term in our derivative function. Okay, so now this is the big rule that's going to give us a lot of, enable us to calculate a lot of derivatives. It's called the power rule. And this is really articulating what we are noticing in the table with the exponents coming down. So we would say if I have some function f of x, which is of the form x to the n, okay? And n is just any number. It doesn't have to even be an integer, even though that's what we've been doing so far. So then we would say f prime of x here is n becomes the coefficient in front. So we have n times x, and then we get a new exponent, which would be 1 minus the old exponent. So it would be n minus 1 as your new exponent. And we can kind of see how this works. Something like x to the third, this 3 is n, so we get nx to the n minus 1, which is 2. This is going to become a really important rule for us. So if we look at some quick examples. First example is going to be f of x equals x to the 5th. So if I'm using this rule, I would say the 5 comes down out front, and my new exponent is 5 minus 1, which is 4. So the derivative of x to the 5th is 5x to the 4th. Now I'm going to show you how we can use this with some a little bit weirder examples. So suppose I have f of x equal to 1 over x to the fifth. Well, the derivative is not just 1 over 5x to the fourth. Instead, I need to get this into the form x to some power. Right now it's 1 over x to some power. That's not the same. This is where our algebra comes into play. So I know this is the same thing as saying x to the negative 5. And now I have something of the form that I want, right? So I have x to the n, where n is negative 5. So I would say f prime of x is, I bring the negative 5 out front. My new exponent is negative 5 minus 1, which, be careful, is not negative 4, it's negative 6. So then my derivative is negative 5x to the negative 6. The power rule also allows us to deal with roots, because if you remember, if we have something like f of x equals the square root of x, the square root of x can be rewritten as x to the 1/2. And now I can think about it as x to the nth, where n is 1/2. So then I would say f prime of x is, I bring the 1/2 out front, then I have x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. And then I could also rewrite that. So if I wanted to rewrite this, one thing I could do is I could get rid of my negative exponent, which would mean that x to the 1/2 would move down into the denominator of this fraction. And then I also know that x to the power of 1/2 is the same as a root. That's how I started. So I could rewrite this as 1 over 2 root x. Just so we do a little bit more exponent review, look at a little funkier example. If I have f of x equal to x to the negative 2/3, then this would become f prime of x is equal to, I could bring this down again, so I get negative 2/3 x to the, now if I have to do negative 2/3 minus 1, I'm going to do like a little sidebar, just so we can kind of think about this. Negative 2/3 minus 1. That is like saying negative 2/3 minus 3 over 3. So it's going to be negative 5 over 3. Now, if I wanted to rewrite that as not having a negative exponent, I could, and also being in the as a root, I could write this as negative 2 over 3. Now, the way you deal with these fractions is the 5 is going to stay an exponent, but the over 3 is going to become the cubed root. So we get negative 2 over 3 times the cubed root of x to the fifth. Okay, so I'm going to give you one you try problem to try on your own before continuing. So your you try problem is going to be f of x equals the square root of x to the third. So can you find the derivative of that? You're going to have to convert this into a fractional exponent. All right, so I'm going to keep going, but you should pause and give that a shot, and then you can resume the video. So the last rule I'm going to discuss in these notes is something called the constant multiple rule. And we already saw this come into play. The constant multiple rule, I'm just going to show you the chart again, is when what happens if I have a constant out front of a function, so something like 5x squared. Well, essentially what we did, if you think about our power rule tells us the derivative of x squared is 2x, and then I'm multiplying that 2x by the constant of 5 to get 10x. So essentially all we're saying with the constant is we just take the derivative the way we would have of that function and then multiply it by that constant. So if I say g of x is some function that is c, a constant, times some other function f of x. Then we would say g prime of x is exactly that constant times the derivative of the f of x function. So looking at some examples, something like f of x equals 3x squared. So I can think of this as the constant of 3 times the function x squared. So it would be 3 times the derivative of x squared, which is 2x, which is the same thing as 6x. Now, as you get better at this, you probably won't need to do this intermediate step. You'll just kind of think about 2 times that 3 becomes 6x. Okay, let's look at another example. So f of x equals 2 over x to the third. So again, I need to rewrite this with negative exponents. So that would become 2x to the negative 3. Now I can think about this as being the constant of 2 times x to the negative 3. So if I was finding the derivative of that, it would become 2 times, oh, I just realized I made a mistake up here in that like this isn't equal to this. So like this is actually f prime of x equals that part. Sorry about that. So anyways, back to this one. All right, so we did 2 times the derivative of this function, which would be negative 3x to the negative 4. Now, multiplying that through, I would get negative 6x to the negative 4, which is the same as negative 6 over x to the 4th. So a U-try problem for you guys is f of x equals 1/2 x to the 4th. So what can you do with that? And actually, I said I wasn't going to do any more. I said this was the last rule, but I'm going to put one more rule in this video, which is something called the sum and difference rule. So the sum and difference rule says that if you have some function h of x that is the sum or difference of some other functions, so we're like adding or subtracting f of x and g of x, then h prime of x will be exactly just the sum or difference of the derivatives of those functions. So for an example, okay, so we have the sum or difference of 3 different we can think of each of these as a different function, so I just am taking the derivative of each term separately. So 4x to the 5th, the 5 comes out front, gets multiplied by the 4, becomes 20. X, my exponent gets bumped down to a 4. My next term, I'm going to keep my negative sign. Now I'm saying the 6 comes out front, was multiplied by the 3, becomes 18. X to the 6 gets bumped down 1 to 5. Plus 2, the 3 comes down and gets multiplied by the 2 to become a 6x squared. Okay, and now I'm going to give you one more U-try problem to do. And it is f of x equals 1/2 x squared plus 6x minus 7x to the 3 over 5 minus 4 over the 4th root of x. So I know this looks a little bit long, but you can just kind of treat each term separately and try to figure out what's the derivative of each term and then add or subtract them all together. And we'll definitely be practicing this next time we have class.